Okay, so welcome everyone to our final talk for the semester at the NCGNT seminar. So it's my pleasure to introduce Alistair Miller, who will talk to us about correspondences, homology, and K-theory for étale groupoids.
All right, thanks. So yeah, this is going to be a talk, I guess, from a sort of C-star perspective, so about C-star algebras, but also about groupoids. So really the sort of, the things sort of ultimately want to understand are C-star algebras. And the C-star algebras we want to try and understand are the ones that come from groupoids. So in C-star algebras, we like to build C-star algebras from other things and use those things to help understand the C-star algebras we just built. And so one of the big constructions that we like to do is groupoids into C-star algebras. And for some context here, there are some, really this captures a lot of C-star algebras. So if you want a sort of technical result, there's this result that says that every sufficiently nice C-star algebra, in the sense that it can be classified by some data, is going to come up as a groupoid C-star algebra, plus a few kind of minor details. This is why we want to understand these, and we want to understand in terms of the groupoids. And then what I'm going to be focusing on is something called the K-theory. So two C-star algebras, we associate two abelian groups, K0 and K1. And these are also going to tell us a lot about the C-star algebra. So this is usually when you try to classify C-star algebras, then you're going to be interested in the K-theory groups as one of the main parts of the classification. So this often remembers a lot about the C-star algebra you started off with. So from a C-star perspective, that's why you do this. From other perspectives, then these K-theory groups of C-star algebras are just good receptacles for things in general, like there's index theory stuff that you do. So this is the diagram I want to understand. This construction is called the reduced C-star algebra of a groupoid. And because of because this is a very general construction, and because this construction remembers a lot, this is going to, in general, be very hard to understand because it contains a lot of complicated situations. So you're not going to be able to get a nice clean computation of the K-theory just in terms of this guy here. But we can try. We can do the best we can. We can develop tools that help us in specific cases. And that's really sort of what I want to do here. Right. So I'm going to expand the diagram a little bit. I'm going to work with a slightly easier class of groupoids. So these are called ample groupoids. And here, groupoids sort of combine together sort of space and groups. So here the point is the space is totally disconnected. It makes this, it removes a lot of topological difficulties working with totally disconnected spaces. And in particular, we have this nice homology theory for these groupoids. So this is sort of the diagram I want us to understand. And the point is that there should be, there's going to be some relationship between these guys. So the idea is this is sort of in principle more computable than this thing up here. So if we can understand this relationship nicely, that will help us with the above diagram when we're working with these guys. And this is sort of, this is the topic that I want to talk about. And there's two. So one of the questions I want to ask is sort of what morphisms work well here. So the point is this is like a diagram of functors or things that want to be made into functors. And so I want a nice notion of morphism of these groupoids that's going to give us morphisms there and make everything work. So maybe I should clarify a little what I mean by groupoid. So the way I'm going to think of a groupoid is that I have a distinguished space, G0. These are topological groupoids. I'm working with everything's topological. So this is a topological space, G0. The elements of the groupoid are arrows that I draw on G0. So an arrow has a source, in this case X, and a range, Y. And if another arrow is sort of matched up nicely, then I'm going to be able to compose them to get HG, I think. And then, as suggested by the group bit of the name, we have sort of group-like axioms for these arrows. So we have this composition that's going to be associative, and we're going to have identities. So at every point we have some identity. And we're going to have inverses for these guys. So this is G inverse here. And you want all of the group-like axioms to hold with this structure. So that's how I'm thinking of groupoids. I just want to stress that I sort of think of the elements of a groupoid as arrows which I draw on this unit space, and then everything has a topology. So I'll write G and H and stuff in G. Okay, cool. So if we have just one point, we have a group. If we have just identity arrows, we have a space. So groupoids sort of cover both spaces and groups. So I'm just going to explain a bit of the subtlety here with the morphisms, because the obvious notion of morphism usually when I give you something which is like a set with a structure is structure preserving maps. These aren't going to work nicely here. So the obvious thing would be continuous homomorphisms of groupoids. But if I've got a continuous homomorphism of groups, like this is going to give me, so if I look at the top row of this diagram here, I want to make this functorial. This is going to give me something of the group C-star algebras in this direction. So we're good. But the problem is if I've got a continuous map of spaces, then I'm really going to get something in the other direction. So let's say these are compact spaces. I'm going to get something in the other direction. So if you do structure preserving maps, you're going to get a sort of wrong wayness. You're not going to be able to solve this problem that part of your construction wants to be covariant, part of it wants to be contravariant. So that's what these correspondences are going to do. They're going to form a kind of morphism of groupoids, which is going to work nicely with this diagram here. Right. So, yeah.
So from your point of view, what are the objects you're primarily interested in? Are they the groupoids or the C-star algebra?
I probably find myself more interested in the groupoids.
Right. I guess what I'm asking is whether if you're interested in C-star algebras, whether you're trying to find some nice models via groupoids, or whether you're interested in groupoids, whether you're hoping by the C-star algebra construction to somehow learn something about the groupoids. Does it work that way?
Right, yeah, good question. So I guess, yeah, the K-theory of the groupoid C-star algebra is telling you something about the groupoid, and that's what I'm interested in trying to understand. I'll probably justify that by saying that lots of people interested in C-star algebras will be interested in the groupoid C-star algebras because they're like, oh, I can find a groupoid model for this thing, and then I can maybe use something. I can use the groupoid model to tell me something about the C-star algebra. In particular, if there are K-theory techniques developed for groupoid C-star algebras, that will help me say something about the K-theory of this C-star algebra.
Yeah, okay, right, thanks.
Yeah. Cool. So, right, I'm just thinking, maybe I won't have time to go through too much technical detail about what correspondences are. No, so I'll give you. Right, okay. So I've shown you here why the sort of naive thing doesn't work. But one thing that's had plenty of success is something called Morita equivalences. So this is a Morita equivalence of groupoids. And what it leads to is a Morita equivalence of the C-star algebras. So we want to view these Morita equivalences as morphisms, even isomorphisms in the category that we work with, because we know that they work. And when we've got a Morita equivalence of C-star algebras, this is actually going to give us an isomorphism in K3. Yeah, so here is the reduced. Here, technically, I have to take the full. If I want to add some analytic details, I can improve this to the reduced. But for the purpose of my talk, the distinction doesn't matter too much. So the point is, I want these guys. These are good. There's also another kind of morphism that is seems to be sort of rediscovered in a bunch of different places, just because it seems incredibly natural. And what it is you have an action. So groupoids, like groups, can act on spaces. You just have to have a little bit more data. You have to make sense of, okay, I want this arrow to act on this space element and push it somewhere. But with groupoids, you can't always multiply just anything together. So you have to have something that makes sense of when is this arrow allowed to act on this space element. And that information, so let me just do it on this one over here. That information is sort of governed by, you have the unit space of the groupoid with the arrow here, and you have the space X that you want to act on. You've got your point X. You want the groupoid element to act on this thing here. What you need is something called an anchor map, which goes from the space to the unit space here, tau. And the point is, if the anchor here matches up with the source of the arrow, you're allowed to act on this and bring it to some g dot x, which is then going to match up with the range here. So this is the extra information that you need for a groupoid action, and otherwise it's just like a group action. So that's what this is. We're acting on the underlying space of arrows of H in a way that's going to commute. So H acts by right multiplication on itself. So these actions are going to commute. It's not going to matter which arrows you do in which order. This is called a Zakrzewski morphism. Also known as an actor or an algebraic morphism. Those are three of the names I know, or those are the three names I know, and probably other people know them by other things. So in the case of a group, this is just the same thing as a group homomorphism. So say this, if you have a homomorphism from gamma to lambda, that's going to give you an action of gamma on lambda by pushing through the homomorphism. And it turns out to be the same information. And for spaces, it actually recovers a backwards continuous map. Because when you have a space acting, all you really have is this anchor map, which is backwards. So we fixed our directionality issue. And these actually give us star homomorphisms. And it's going to be into the multiplier algebra of the second one, but then you can ask for a condition that will, much like with continuous maps of spaces, you can ask for a condition that will make sure you get something on the level of the C-star algebras themselves.
Could you say again what kind of map this anchor map is?
It's a continuous map. Yeah. Yeah.
You just consider it as a topological.
Right, exactly. Yeah, so this is sort of the space of arrows, if you want, in H. Is one way you can help to just yeah, make sure that it's the space we're thinking about, not the. So we're not trying to act by groupoid automorphisms or anything, just as a space. Yeah. So these give us good maps on the level of C-star algebras. An easier one I should have probably given before was if you've got an open subgroupoid. Then this gives you an inclusion on the level of the C-star algebras as well. So the point is, each of these different kinds of morphism of groupoids is going to give me something good on the C-star level, and correspondences are a common generalization of all of these. They're sort of what happens, yeah, when you, and then every correspondence is going to be some composition of these guys. So let me give you definition of a correspondence. So an étale correspondence. So the groupoids I work with are called étale groupoids. What that means is they're sort of discrete in the group direction. So I only have to worry about the topology of G naught. Technically, it means that this range map that takes me from an element G to its source, say, or its range equivalently, is a local homeomorphism. All that's telling me is that the topology on the arrow space can be recovered from the topology on the unit space. So the group direction is discrete. That's the sort of. So I'm working with étale groupoids. So it's a bispace. So I've got an action of G on omega and an action of H on the other side. And I'm going to give the anchor maps names. So the anchor maps go into the unit space. Here, this is going to be rho for range, and this is going to be sigma for source. So being a bispace means that it doesn't matter which action I do first. So if I am allowed to write G dot omega, and I'm allowed to write omega dot H, then this is gonna hold. So that's what it means to be a bispace. And then I'm going to have this condition that this right action is super nice. And it's not really going to be important for the talk what this exactly means. But free, proper, and étale. So if you know what free and proper mean for group actions, this is very similar. And étale is a purely groupoid action thing because it's exactly saying that the anchor map is a local homeomorphism. But feel free to forget that. It's not going to be important for this talk.
But so the anchor map always has to be defined everywhere on. Yes.
Yeah. So my convention for a groupoid action is defined everywhere on X. You could.
You could take an open subgroupoid and that would still be the morphism, and then this example you had where you had an open subgroupoid just as inclusion, like viewed as a particular case, but.
Yeah, I think. Yeah, so there's basically two ways of doing things in some respects. I'm happy to change my space. If you care that your space is a particular space, it might be convenient to start looking at things where the anchor map is only defined on a certain part of it. Right, but I think you can get those here anyway.
Okay.
I think. Yeah. Like it really is just I'm happy to change the space, and then you can. I think there's some like two ways about that. Because I think you're thinking if you're in this situation here and you allow for the more general thing, then you can consider what that'll be equivalent to is considering some subset of H1. Basically the subset on which the anchor map is actually defined. And then that would give you and end up giving you the same sort of things at the level of the C-star algebra. But yeah, that's another thing you can do. Right, so this is the definition. And hopefully, I've not told you what a Morito equivalence is, but what it is, one way you can define a Morito equivalence of groupoids is like this, but more symmetrized. So you ask for both actions to be free, proper, and étale. And you ask for, how's this? So the anchor map on the left, the range anchor map, and actually both, because it's bispace, it doesn't matter. It's constant on any orbit, on any H orbit. So now we get a map from this space here of the H orbits to G naught, which is going to be continuous. So a Morito equivalence is where you symmetrize all these things and you ask for this to be a homeomorphism and also the other one, the sort of symmetrized one, to be a homeomorphism. So that's exactly what a Morito equivalence is. So then hopefully I can sort of convince you that all of these are going to be some example of this thing over here. And open groupoids also fit into this because you can let morally you put H in the middle still, but this is exactly this thing Tristan talked about where you might have to reduce to a smaller subset here. So I'm going to have to, this notation here means that I only look at the arrows in H whose range lands in G naught. And that's what's going to make this all work. So in all these three cases, I have something that looks like this. And I'm going to call omega proper if this continuous map is proper. And this is going to be the analog of a proper map of spaces, which is what gives us something on the C-star level when we take a C-star algebra out of a space. So if you have a proper map X to Y, you get star homomorphism from the C naught functions on Y to the C naught functions on X. And it's exactly the same sort of thing going on here if we ask omega to be proper. Okay. So so a result by I guess in this sort of framework, this is okay. I'm going to attribute this to multiple people. So this is originally done in a slightly different setting by Holkar and done by Tunis, Cole, and Maya in the étale setting, in the more general étale setting. And it basically says that so yeah, étale correspondences functorially induce C-star correspondences. So I've not told you the composition of correspondences, but it's some way of sort of smashing bispaces together over the middle groupoid. Yeah. And then you can do a similar thing on the level of C-star algebras, and this is going to be functorial. And the point here is that this preserves properness, and proper C-star correspondences are also known to give you maps in K-theory. So if we take proper correspondences over here, we get proper correspondences here, and we get maps in K-theory. So this is what sort of sorts out the top level of the diagram. Yeah, so I don't think you can say this is. Yeah, no, I don't think this is. There's no. The problem of taking a C-star algebra and reconstructing some kind of groupoid is one that people study. You typically what you need is more data and special kinds of C-star algebras in order to rebuild groupoids. Yeah. But yeah, so really this is saying that this actually is a functor. This is sort of, yeah, so this thing here is part of their construction. Yes, go for it.
For example, like bundle of groups and also is the bundle of groups. And then it's means that this always means that all of these fibers that is the group that acts on the some space like omega, and also all of these edges that are groups also acts on the omega. And then we can say something in special case or correspondence here. I mean,
I'm not sure. I've not thought about this. So I mean, if you have a bundle of groups G acting on omega, then that means that you split omega up into you've got some anchor map from omega to the X, the base space of the bundle, say. And then each group is going to act on that fiber within omega. So omega is going to be fibered over the space. So for each point you have something, and G is going to act on there. I don't know what you can say.
so but even if the transport we cannot characterize that. I mean the correspondence between G and H are come from the group actions and so on. Even imagine that we have two groups that acts from left and right in some specific space.
Mm-hmm.
And actions for group and then we have two correspondents. We can characterize that. So we have two groupoids. We can say something that's what type of the correspondence can be between them.
I'm not sure. No, I don't know.
But there are some natural examples of correspondence.
Right. So yeah, so maybe something I want to stress is that these Morita equivalences are examples of correspondences. Morita equivalences you find in, so the fact that when you take Morita equivalences, your K-theory doesn't change. This is very important for lots of papers that are trying to compute K-theory. They'll end up using this fact about Morita equivalence maybe on the groupoid level, maybe on the C-star level, a lot. So you see these particular correspondences quite a lot. Open subgroupoids, you see these a lot as well. This certainly, these are all over the place. The fact that you combine them together, sort of, at least in some of the things I've worked on, is quite natural and helps just sort of. So yeah, these appear in a lot of places, and these guys appear more often than you'd think. So maybe I can give you an example actually. I should have given some more examples of these. So one thing is that if you have a groupoid acting on a space X, so you can form a transformation groupoid of this. In the same way that you form a transformation groupoid of a group action. And now you get G acts on the transformation groupoid by sort of just translating this bit, and this acts on itself. So this gets you into this sphere here. So this can be quite useful. So sort of whenever you have an action, you now get one of these morphisms between your original groupoid and your action groupoid. There's also a case where you have some nice kind of homomorphism. So if this is proper, surjective, and something called fiberwise bijective, then you can actually build from these conditions. You can build from these conditions a natural action of G on H. Yeah, homomorphism. Thanks. So when this is a proper surjective, fiberwise bijective homomorphism, which is a lot to say, you get one of these things, and these are actually so you get in particular an inclusion of the C-star algebras from these guys. Yeah, I think inclusion, at least a map of C-star algebras, and these are the guys used in Xin Li's proof that every classifiable C-star algebra has some groupoid model. So in the sort of abundance of groupoids proof, these guys are used, which I guess sort of the moral is these are quite abundant. So yeah, I don't think there's any sort of, I don't think there are any results on sort of characterizing correspondences between things, but the point I want to make is that there's lots of them. So I don't know if that answers the question. All right, so point is, if we start off with proper correspondences here, we can get proper correspondences here. And we'll get homomorphisms here. So we've sorted out the functoriality on the top level. If I add in these here, one of my results is that yeah, I'll just state it in the same way. So étale correspondences of ample groupoids functorially induced maps in homology. So these homology groups, we have a homology group for every natural. And these are going to tell us something about the groupoid. But I guess for the purpose of this talk, we're interested in them because they relate to the K-theory. So okay, so we get homomorphisms here, so that's good. We've made all of the diagram work, except we don't know what this relationship is yet. And this is why I'm going to be interested in them for the purpose of this talk. But I think there are good reasons to be interested in this homology, but for other things. There are some relations to homological properties of quite interesting groups. So there's a construction from ample groupoids where you start off with a boring ample groupoid and you construct a very interesting group in a particular way. And then there's some relationship between the homology of this guy and the homology of the interesting group that group theorists even care about. So that's one direction but that's not the direction in this talk. Okay.
So what is the homology for groupoids, or are you about to explain that? Maybe.
Yeah, I can give you a sketch. Yeah, let's do that. So I want to keep this board here and up. Is it okay if I rub this out? Yeah, this one's in front, and maybe, yeah, I'll give a definition down here. I think I've got space. So groupoid homology. So if X is totally disconnected, I'm going to write ZX for the compactly supported Z-valued functions on X. So ZG is a ring. Well, it's a locally unital ring, so it doesn't necessarily have a unit, much like C-star algebras aren't unital. Necessarily, they just always come equipped with approximate units. This is a locally unital ring with convolution. Which, in the case of us, yes. So yeah, so now if G, so G is an ample groupoid. Sorry, yeah, G is always a groupoid for me. Now it's ample, which means it's totally disconnected. And now we can put a convolution structure on this. We can put a ring structure on it with convolution. And this convolution is what, if you were working with a group, this would basically just be like playing out the group multiplication, but on the level of the functions on the group. And that still works when you work with a groupoid. So it's using the groupoid multiplication structure and turning this into a ring. And to construct the C-star algebra, by the way, you do a very similar thing. You just work with the complex numbers instead of the integers here. But the point is, now we've got a ring, we can do ring theoretic homology stuff. So we get module categories of left modules and of right modules. I should have written them the other way around, because if you take a right module and a left module, you can tensor them together to get an abelian group. So if you've got M here and N here, then N tensor GM is an abelian group. This is something you can do. And a source of modules is if you have an action on some space where this is totally disconnected, you get an action. You can write down a sort of convolution thing using the action on this abelian group here, and this gives you a G module. In particular, you get a trivial G module. Where the groupoid acts on its unit space. Here the point is an arrow is only going to act on one point. The anchor maps the identity. The arrow is going to send its source to its range. So this is like the trivial action. It's like the analog of a group acting on a point trivially. Now, if you know enough homological algebra, then you'll have seen Tor functors. And the groupoid homology is that. So I guess this is I for I equals 0, 1, 2, ... We can do it with coefficients in a G module. Here, this is M. This is Tor, ZG, like this. And if I want to just refer to the groupoid homology without any coefficients, I plug in the trivial module on the right here as well. And yeah, I don't think I have enough time to really go into what exactly this Tor thing is, but this is a very classical construction in homological algebra that relates to the tensor product here.
So if G is trivial groupoid, then the homology groups
Right. So if G is just a space, so just a totally disconnected space, then the homology groups are going to be. So I'm just going to find some space. So if G equals G naught, then HI of G. So now I'm not writing any coefficients, just to mean I put the trivial thing in here. This is going to be Z G naught for I equals naught, and it's going to be naught for I greater than naught. So it's the same thing as the K theory of the space. Yes, exactly. So this is groupoid homology. Right. Where's the? It's usually good if I wet it.
Whatever works for you.
Okay. Oh, that was too wet.
Could be a squeaky.
Okay, I think we're good now. So, okay, that should be fine. So G, an ample groupoid. We're going to say G satisfies HK. The HK property, I guess. If, when we take the K theory of the C-star algebra, maybe I'll just put a star here. No, I'll put an I here. This I is equal to 0 or 1. So the reduced C-star algebra of G, take the K theory, then this is going to be isomorphic to if I add up all of the homology things with the same parity of the groupoid. And there's a natural number, which includes 0. And the point is, this actually does happen sometimes. So basically, Matsui came up with this thing, and under some conditions, he conjectured that this might. Well, he conjectured that this might happen under certain conditions. So many what's called topologically free examples from topological / symbolic dynamics. So these groupoids are sort of a nice way of collecting together lots of different examples that come from various places. So you can get them from combinatorial things, you can get them from algebraic things, you can get them from dynamical things. And that's this sort of class here. So if shifts of finite type mean anything to you, these are some of the things that he verified that the groupoids that you get from shifts of finite type satisfy this. Okay. But it's not true. So Eduardo Scaparo came up with a counterexample. And really the point of this counterexample is that there's torsion in the isotropy. So the isotropy of a groupoid is all of the arrows that begin and end at the same point. So it's a group. You get an isotropy group at each point in the space. And if there's torsion in that group, there's torsion in the isotropy of the groupoid. And the problem is that's going to completely mess with this, turns out. But worse, there's counterexamples even without any isotropy. It's just that it's 9-dimensional in some sense. So this is quite big. And indeed, his PhD student, so Robin's PhD student, Rachel Chaser, has a 4D version of this. And the point here is that anything too high dimensional, this is much too simple a relationship to expect. This is, a vast oversimplification of what's going on. 9D. So what it's going to mean is that the homology will vanish for degrees 10 and above. That's one consequence of the 9-dimensional, but I'm being a bit vague here. They sort of take some stuff. They perform this construction where you construct some ample groupoid out of some 9-dimensional or some manifold with some structure, something. I can't remember the details of the structure, but when you're in the manifold world, it literally is 9-dimensional. And that has consequences which sort of makes it feel 9-dimensional in some sense over in the groupoid world, but I don't know if there's like a way to be concrete about that. And yeah, and this was done with a 4-dimensional manifold.
So there's no, like, between K theory and homology, there's a rational, tensoring.
Right.
There's no hope for this.
Well, there's hope for that. This relationship here is much more realistic after tensoring with the rationals. So if someone were to go and construct some kind of Chern character, this would be sort of plausible rationally, as long as you kill as long as you don't have any torsion in the isotropy. This counterexample like messes with this entirely. This one doesn't mess with it rationally. And actually, Robin and Rufus Willett have proved the rational version of this in the transformation group setting under some conditions. So but you have to assume no isotropy, no torsion isotropy, at least, because then this will mess you up. So there are some. So the positive results we get are really sort of you assume torsion-free isotropy. Let's say just put amenable here for now. We need H2 to be free abelian, and we need H3 plus to vanish. And I think that's enough to say you need Hausdorff-Miss is sort of an implicit assumption in a lot of this, but not all of this. So I'm not going to go into details of when and where. But basically, that's good enough. And I'm not going to write it down, but I'm going to say in words. What they actually do is you prove there is a spectral sequence. So they construct a spectral sequence whose second page is given by the homology, and it converges towards the K theory, assuming the Baum-Kohn conjecture for the groupoid. And the way to think about the spectral sequence is that what it converges to, the K theory, is somehow built up out of the thing on the second page, the homology. And it's more complicated than a direct sum, but in low dimensions, it does sort of look like a direct sum. And also rationally, it's going to sort of look like a direct sum if you have some kind of map the other way, some kind of Chern character. So that's sort of how these ideas all tie in together. But yeah, I think now got 5 minutes left. I've got enough time to state my theorem. I hope. So basically, it's Valerio and Makoto's work that I sort of build upon. And the point is, if we go back to the diagram, this sort of has like a very rough summary of the relationship here. The real relationship is you've got some spectral sequence converging to the K theory. And this is sort of like the homology here. This is the actual relationship that's going on. And what I do is I make this functorial with respect to correspondences. So it sort of provides some sort of natural transformation from homology to K theory in some sense. But the sort of a consequence of this let G and H be, I'm going to write PY to just mean, no, I don't want to write that. So torsion free, amenable, but if you know what it means, it's enough for them to satisfy the Banach conjecture. So torsion free isotropy, amenable, Hausdorff, and let omega from G to H be a proper correspondence such that you get an isomorphism in homology. I'm just going to write it like this. So it induces an isomorphism in homology. Because if we had the HK conjecture, we'd then get an isomorphism in K theory automatically. What I'm saying is you don't need this. You can just use the more complicated relationship here. Oh, water bottle. Sorry. Then you're going to get an isomorphism in K theory. And the point really is that these assumptions here are much weaker than this thing that's going up on here. Because really, what these guys did was sort of clarify what this relationship actually looks like in much fuller generality than this sort of simplistic model here. So the point here is now we can do stuff on the level of homology, which is easy, and deduce things about K theory, which is hard. So as a corollary, there's a particular kind of C-star algebra that we can now compute the K theory of, or reduce the computation. So this is built out of something called an inverse semigroup, which, if you don't know what it is, it's like an algebraic structure of partial symmetries in the same way that a group is an algebraic structure of symmetries. So think partial bijections on a set, which means you take two distinguished subsets and you put a bijection between them. But we can make a C-star algebra, and I'm going to add some conditions orally, which basically just mean that when you build a groupoid out of this guy in the usual way, you get something that satisfies these. And there's a C-star algebra we can associate to these guys as well, by the left regular representation. This guy is going to break down into a computation of the groups of the K-theory of group C-star algebras. So now, just mindful of time, I'll write this formula down and I'll just sort of explain in words what's happening. Maybe I'll write this as well. So what do we have here? So we have an inverse semigroup. It's not going to have. So these here, these E's are idempotents in the inverse semigroup. This is like, if you're thinking of partial symmetries, these are the identity on some specified subset. And each idempotent can act as the unit for a group. This is sort of the maximal subgroup of S with unit that idempotent. So you've got a bunch of groups sitting inside your inverse semigroup, and this is telling you that the K-theory behavior of those is going to determine the K-theory behavior of this C-star algebra here. So these are groups, and calculating the K-theory of group C-star algebras is hard, but at least it's better than calculating the K-theory of inverse semigroup C-star algebras.
So just on the left, you've got what the
Is that the universal C-star algebra of the semigroup, or?
Yeah, so on the left, what I've got is the left regular
Okay,
C-star algebra. So there's a Hilbert space where I take L2 of S. And every inverse semigroup element is going to act as a partial isometry on this Hilbert space.
So it's probably not the same universe.
I've not heard that term before. It's the same as the C-star algebra, the reduced C-star algebra of the universal groupoid.
Okay, so we just use of the universal group. Okay, so maybe this is. And so is that what's on the right? This SE, this is a groupoid or something.
SE is a group.
Okay, so this.
So this is this group here with, it's all the things in S which have, which,
Unitary.
with sort of unit E. So this is actually a group. So often in interesting, there are plenty of interesting examples of inverse semigroups that you want to know the K-theory and use this to help you do some stuff with, where all of these SEs are going to vanish. They're just going to be trivial groups. In which case, over here, you get something very easy. And I should stress that there's a bunch of conditions here that I've not written out, which are designed to give you the stuff up there. Yeah, good question. So this E is the space of idempotents. So these E's here. So E has to be, so I want E squared to be equal to E in the inverse semigroup. And I've just written a cross here because I always want there to be a 0, but I don't want to consider the 0 in this space here. So. And just a moment about the proof of this is that from any inverse semigroup, even without any conditions or anything, I can construct a correspondence, which is essentially going to give me a groupoid on one side, which has K-theory this, and a groupoid on the other side, which has K-theory this. And I can show bare hands that this correspondence gives me an isomorphism in homology, because homology is easy compared to K-theory. And so then this theorem then tells me that I must get an isomorphism in K-theory here. But yeah, I think that's all I wanted to talk about. So thanks for listening.
so very nice talks. Do we have any questions?
You said at the very end there. So you said there are often circumstances in which this K-theory of the inverse semigroup is just trivial.
So there are circumstances where all of these maximal subgroups
Yeah.
are trivial.
Yeah, but does that not have the implication then that the
Right. Then you just get a direct sum over here. You
Yeah.
get a direct sum over all of the orbits of
Yeah.
the thing. Yeah. So yeah, right. So often this sort of tells you that actually the K theory of these guys is then not that bad.
not that but why is it not just trivial? What am I missing here? Like you're saying all of these SCs are just the trivial groups, so the group C.
Yeah, so SEs might all be trivial, which means
Uh-huh.
you get the complex numbers here.
Yeah.
So you get a bunch of
I see,
copies
I
of the
see, I
K theory
see.
of the complex
Got you,
numbers.
got you. Okay.
But a good way to think about these C-star algebras is they're sort of like tuplets type C-star algebras.
Right.
So it's a bit like what's going on here is a bit like the fact that the K theory of the tuplets algebra is the K theory of the complex numbers. And more generally, it's it's sort of morally similar to when you take like some tuplets algebra of a correspondence or something, then you get like a KK equivalence with the base algebra, or you get like K theoretically it's looking the same. And you might often be interested in quotients of this guy, which you can then use this as a stepping stone to try and understand the K theory of the quotients.
And do these, would you expect these quotients to be like classifiable or something, or?
Yeah, the quotients might be classifiable.
Yeah.
This is always going to be highly non-simple.
Sure, like the tuplets.
Yeah.
Right.
Yeah.
Oh, thanks.
So, Crystal, that is said that Dan probably could say something about K groups or groupoids which are not known, and asks, would you be able to give an example? So I guess what they're saying is, yeah, an example, the last thing where you say, oh, this tells you.
Right. Yeah, so one thing maybe I didn't say, but maybe should have done, this sort of formula existed for a particular class of inverse semigroups beforehand, where you have, but only for that class, really. So if the inverse semigroup has what's called an idempotent pure partial homomorphism to a group, gamma, let's say, which basically tells you that the dynamics of the inverse semigroup can be controlled and governed by some group, then this formula, and some conditions, blah, 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 this formula is a consequence of a paper by Xin Li. But this removes sort of the requirement for having this group that governs everything, which on the inverse semigroup level, you can quite easily violate this, because if you talk to an inverse semigroup theorist about this condition, about this group thing, they'd probably tell you this seems extremely restrictive. I think you can do things like, I should. You can sort of draw pictures of inverse semigroups where you like say, okay, say I've got some group here, and I think of let's say my group is lambda, and it's got some idempotent E, so the unit of the group, then this is a group. But I can very easily make an inverse semigroup by just doing something like putting some other idempotent below it. And I think this structure here is going to completely violate any chance at being able to get this idempotent pure partial homomorphism to a group. Because the point is, if you go towards some group gamma, then both E and F are going to have to be mapped to the identity. But actually, all of the elements of this group are going to have to map to the identity. So you're killing a lot of information as soon as you have to go to a group in a sort of reasonably faithful way. So on the inverse semigroup level, it's very easy to violate this thing and thus just sort of draw these examples with your hands that are going to give you examples where this is now a new formula. Don't know if that answers the question.
Okay, any other questions? Okay, if not, then let's thank the speaker again. Yeah, thanks for coming. Hope to see you next semester.